think so. Let's start with right. I would say.
Hi everyone. So my name is Ahmad. I'm a fourth-year engineering science student, and today I'm happy to talk about modulo analog to digital converters for this colloquium talk. So to begin with some general motivation. So the whole problem of analog to digital conversion is very important and is widespread in pretty much all of our modern electronics, all of our modern devices. And basically the main purpose is to act as an interface between the real world and the devices. So first of all, to briefly define what a signal is. So signal can just be thought of as any information carrying waveform. And then there's various different types of signals. One of those types is analog signals, which are basically you think of them as continuous functions of time. So they're both continuous in time, and also they have continuous amplitudes. And then so signals in the real world, they're usually of the analog form. So for example, speech, light, all those are examples of signals that exist in the real world. However, when we want to actually record those signals or process them in our devices, they have to be converted to a digital form because computers, as we know, can only deal with like ones and zeros or bits. So the ADC is so the ADC, like the analog to digital converter, for short form, is denoted by ADC. So this basically is a device that allows you to convert from these analog signals to digital signals such that they can be then further processed in devices and used for different purposes. So basically, like within the ADC, there's two main operations. The first one is known as sampling, and this will be like the focus of my talk. So I'll be focusing on this aspect of the ADC. So for example, if you have a signal, I'll denote it by a function x of t. So a continuous signal or analog signal can just be like any continuous function of time. So the operation of sampling basically records the values of this function at discrete time steps corresponding to some sampling period denoted by Ts. So we basically will record the signal's value at 0, Ts, 2 Ts, and so on. So you just record what the value of the signal is, and that will be like the output of this this process will be a set of values x ATS where k is an integer. And then the other process in an ADC is what's known as quantization, and this can basically be thought of as rounding. So basically, like these values which are like real numbers will be rounded off to a nearby value because you only have a finite number of bits or a finite number of levels that you can represent at the output of the ADC. So one of the main practical limitations of ADCs is the fact that they all have a finite dynamic range. So dynamic range is short form is dr, and this basically represents the minimum and maximum values that the ADC can correctly deal with. So for example, if your dynamic range is, let's say, between here and here, then basically like any values that exist, let's say like you have a value over here. So if this value is outside of this interval, then this value will basically be clipped or be saturated such that what you actually get out of the sampling operation will actually not be this value itself. It will be like some value slightly lower or slightly higher than this. And this limitation causes a lot of distortion and causes the quality of your output signal to be affected quite a bit. So the whole concept of a modulo ADC seeks to deal with this limitation, and the way it does this is it first applies a modulo operation on your input signal that will effectively fold or so that will effectively fold it such that the signal lies completely within the dynamic range. In that way, when you sample this modified modulo signal, all of your samples will all of your discrete samples will be of high quality, and then you can actually use some sort of a reconstruction algorithm to go from these modified values back to the values that you would get if you were to sample directly without any dynamic range limitations in the ADC. So now to first first I'll go over some of the basics from signal processing that are going to be useful later on in terms of actually understanding how this can be done, how the reconstruction algorithm works, and so on. So I'll start with some of the basics. So one of the main main points in signal processing is this whole notion of a time domain and a frequency domain representation. So the time domain, as I just said, is like there's a continuous function of time, say x of t. And then there's an equivalent representation in the frequency domain denoted by capital X as a function of frequency. And these are both basically like equivalent representations of the same function. However, usually doing processing in the frequency domain provides many advantages. It also provides like more intuitive views of signals behavior of different operations that are used throughout the whole field of signal processing. And the way that we convert between these two is to use the Fourier transform. And this is like an invertible transform. So it can formally be defined like this. So x of f is just the integral. So intuitively, this is like can be thought of as a decomposition of your signal into its frequency components or into complex exponentials. And overall, the whole notion of a Fourier transform is kind of a generalization of the notion of Fourier series. However, to include functions that are not periodic, whereas the Fourier series only deals with periodic signals. So one of the main theorems within signal processing that is also the underlying theory for ADCs is what's known as a Shannon sampling theorem. So this theorem basically like provides guidelines, provides a criteria on what sampling rate or sampling period TS is required in order for your digital in order for your samples to accurately like represent all the information that you had in your signal x of t. So basically like it's possible to go from those discrete samples back to your continuous function. And like this theorem is specifically defined for a specific class of signals known as band limited signals. So basically we say that a signal is band limited with a bandwidth of b if in the Fourier spectrum of the function, if you have that it's equal to 0 for all frequencies above some value b. So like a bandwidth is basically so bandwidth is basically like the endpoints of your spectrum. So if you were to draw your spectrum, then if it has a bandwidth of b, then everything, all the spectral content will lie between those two frequencies. Everything above that will be equal to 0. And like typically for real signals x of t, the Fourier transform is always symmetric about the y-axis. That's why I also have negative frequency components like this, just by convention. However, it's also equivalent to just like focus on the positive part of the frequency axis. So what the theorem says is if you're given some continuous or analog signal x of t that has a bandwidth of b, then the only requirement is that your sampling rate denoted by fs, which is just the inverse of the sampling period, as long as you have that this is greater than 2 times your bandwidth, then all those samples x of kts like fully represent the information that was in the continuous signal x of t. So like specifically, it's possible for there exists a one-to-one map from these discrete samples back to your continuous signal. So in practice as well, ADCs also like use this theorem in order to set their value of TS or FS such that their output is like equivalent to the continuous time signal. So now I'll go towards the mathematical model of behind modulo ADCs. So specifically, the first thing that we're going to do is define a modulo operation. So I will denote that by m lambda of x, and that will be given by following. So this is like so. So this expression looks kind of unintuitive. However, it's just representing a shifted modulo operation. So the standard modulo operation would be, let's say, if we have a modulus of 2 lambda, that would be like this. So if we have our inputs, let's say 0, 2 lambda, 4 lambda, then like just by how the modulo operation is defined, every the output of applying the modulo operation will always bring the value down into the range 0 to 2 lambda. The only difference with m lambda is that instead of 0 to 2 lambda, it will deal with minus lambda to lambda. So everything is restricted down by lambda. So basically, like the final output of m lambda will always lie in this range. And the only reason for doing this is to have a more symmetrical definition, and that makes like the math easier later on. But basically, it's still like the underlying modulus is still like 2 lambda, and this will like our goal here is to set this 2 lambda to be equal to like your dynamic range should be equal to this, such that after we apply the modulo, then the whole signal will be like folded in between this range of minus lambda to lambda. So now basically like I also like define how so like the overall input signal I will define again to be x of t. And then we'll say that after you apply the modulo operation, we'll let the result be y of t. And then because we're focusing on the whole aspect of sampling, we will let the samples of x of t be given by x sub k. So x sub k is just equal to x at k times ts. And similarly, we'll let y sub k be the signal y evaluated at the times ats, and k here is just an integer. So like the overall problem now is after we apply the modulo operation, after we obtain these samples y sub k, we want to go from y sub k, we want to go from that to x sub k, because as we know from the Shannon sampling theorem, if we have these xk and if we meet the criterion for on the value of ts, then we're able to go from xk back to x of t. So our overall goal in this problem is to go from yk, go from there to xk, and then from there recover your overall input that was a continuous time signal. So first of all, one of the first observations that we can see here is that x of k can be decomposed as yk plus rk, where rk is basically like a residual function. So by the fact that we have question,
concerning the Shannon theorem,
yes,
it says if you have some collection of points with intervals small enough, then you can reconstruct the whole signal. But how many points exactly do you need?
Yeah,
because this seems like all.
Yeah. So like it's like like formally this theorem requires all like points from negative infinity to infinity. However, even if you have a finite number of them, like it's like even a finite number is able to still produce a very like good approximation to the whole signal. So like formally it requires like for all time, but like even if you have a finite amount of time, it's still a very good approximation to the recovery. So like the recovery is still like very good quality, and that's.
But it's not that finite. There exists some finite number that will reconstruct the whole thing. It's only some approximation.
Yes. Because basically like so actually like the reconstruction is normally like done using some sort of a what's called a sync interpolation. So overall that interpolation like defines an infinite sum. So you have to compute an infinite sum in order for you to obtain the value. However, for large values of t, those values often become very negligible. So having them or not having them in the sum doesn't really affect the quality too much. So the first observation is that you can decompose the samples xk as yk plus rk, and by the fact that y is just a modulo of x, we also know that rk will always take values that are multiples of 2 lambda, because r is like the difference between x and y, so it's like equal to like the difference between a value and the modulo operation applied to the value. So we have like this. This is an important property. And now we'll overall let me raise the order. So for the actual recovery algorithm, we'll first define a operation known as the finite difference operation. So I'll denote that by delta. So specifically, we'll define like delta, let's say y at index k will be equal to y at index k plus 1 minus y index k. And this can also like be extended recursively. So you can define the nth finite difference of y at index k to just be the n minus first finite difference of y minus the n minus first of at index k minus 1. So we can also consider a simple example of this operation. So let's say our samples y. Let's say we have 4 of them, and let's say those are given by let's say 0.1, 0.4, minus 0.7, minus 0.5. So applying this delta operation will just like compute consecutive differences. So we have 0.4 minus 0.1, 0.3 minus 1.1, 0.2. And then if you apply this operation one more time, that will basically like give minus 1.4 and 1.3 as your values of delta squared of y. That's how the operation is defined. So now I'll make the following claim. So the claim is basically that if you start off with a band limited signal x of t that has a bandwidth of b, then we have that the following bound holds. So the maximum value of the nth finite difference of x, denoted by like the infinity norm of the nth difference of x, is upper bounded by your sample period Ts times 2 pi e times b raised to the power of n, multiplied by the infinity norm of your continuous function x. So basically, like I won't be going over the proof of this over here because it takes some time, but it can be done using Taylor's theorem and using Bernstein's inequality that quantifies like the maximum rate of change for a band limited signal. So why is this like claim actually helpful for us here? It's because we can, by choosing capital N and our sampling period appropriate, we can basically like guarantee that this right hand side is upper bounded by any value that we want to. And what we'll do here is we'll upper bound it by lambda, because as we saw with the definition of the modulo function, like any value between minus lambda and lambda is unaffected. Question.
I was thinking if you could do this, is that the operator norm? Is that same?
Yeah, it's like
Sorry, I was just thinking if that's same as operator norm. You can.
oh yeah, so over here is actually like so like the infinity norm is just like a maximum, like the maximum absolute value at any.
I was trying to think if the operator norm of the delta is not accurate.
Yeah, that could also be considered. I haven't actually like considered the operator norm of delta. So I'm like this, like these bounds only focus on the infinity norm. So what we'll do now is we'll set this right hand side to be equal to lambda. Then you can see that if you have that n is greater than or equal to log base ts 2 pi e b of lambda divided by the infinity norm of x, and if you have that that ts is less than 1 over this, such that the whole product is less than 1, then this, like setting these two conditions, will guarantee that the nth finite difference of the samples x is upper bounded by lambda. Yeah, so actually like biggest over here like corresponds to like discrete samples of the continuous function x. So it's like defined further. Like capital XK is just the value of the function or signal x at those specific time steps. It's not. No, it's actually not. So from here on out, there will we won't be beyond the fact that we just have a finite bandwidth. We won't actually be dealing with the frequency domain. Everything is like in the time. So you can like specifically, if you simplify this, you can like n is always an integer, so you can also just like set n to be like the floor ceiling function of. If you simplify this expression, it will just be following. So from here on, like we'll fix our value of n to be this. Now, by this bound that we have, we're able to like simplify some things and get some interesting observations. So basically, like from that decomposition that I had, just to summarize, like the samples x are always samples y plus r. So if you apply this nth finite difference on both sides, because the nth finite difference is also like a linear operation, so you'll just get that delta n x k equals delta n y k plus delta n r k. And now we can also apply the modulo operation m lambda on both sides, because that's also a linear operation. So we obtain that this is also true. And now, as long as we choose n and ts to satisfy these conditions, we know that this is always bounded above by lambda, and that would mean, by the definition of the operation m lambda, that this is just equal to delta n xk by itself. This one over here we know is just equal. We just leave it as it is. And then using the fact that r is always like the values in r are always integer multiples of 2 lambda. So computing the finite difference of that also like results in multiples of 2 lambda, because you're computing the difference between values that are themselves integer multiples of 2 lambda. And that would mean that after you apply the modulo, because any multiple of 2 lambda will just go to 0, so this will always be equal to 0. You have this. So overall, we have like this identity just by simplifying and using this bound. Now, what this means is, if we go back into this equation here, we're able to like see that we can compute the nth finite difference of r. We can compute it just as, if you substitute this over here as the modulo of y minus delta n of yk. So overall, like only by using the modulo samples y, we're able to compute nth finite difference of r for any index k. And like as I mentioned before, in order to do the reconstruction from y to x, it's equivalent to first find r and then just add y and r that would give you x. So the way this algorithm will proceed from here on is it will basically like start from this and try to recover r by itself by effectively like undoing this finite difference operation. So what we want to do is we start from knowing delta n r. We want to go to like delta n minus 1 of r, so on, delta n r, and then we'll go down right to delta or the first order finite difference. And the way that this operation will be done is basically by using the anti-difference by an anti-difference operation. So kind of like the opposite of the finite difference operation. So specifically, so I will define the operation using capital S, and this, if you apply this to any, like let's say a vector of values or a set of values v, then this sum at index k is going to be equal to like one of two possibilities, either 0 if k equals 1, and if k is above 1, it will just be like the sum of the previous values. So from 1 to k minus 1 of vi. So it's kind of like a discrete version of your discrete version of integration. Because the finite difference operation is kind of like similar to differentiation, but using only discrete values. So the way that we'll define the operation. So this will also consider a similar example that we had before. So if we arrived at minus 1.4 and minus 1.3 after doing the finite difference 2 times. So now if we take the anti-difference of this, that will produce 0. Then the second value will just be equal to this, minus 1.4. The third will just be equal to this plus this. And so basically, oh, sorry, this is 1.3. This will be minus 0.1. So similar to how integration produces a constant of integration, this also produces a constant, like it produces an unknown constant that has to be recovered in order to proceed further. So in this case, like we had over there, let's see. So we had like 0.3 minus 1.1, 0.2. So that means that here the constant of integration is like 0.3. So if we like, let's say we know this constant of integration, then we can go from here, just like make it the correct value, 0.3 minus 1.1, 0.2. And then if you apply the anti-difference operation one more time, you can obtain the following. So 0.3 minus 0.8 and minus 0.6. And in this case over here, like we had 0.1, 0.4. So our unknown constant in this case is equal to 0.1. If you apply that, then you'll get the same array that we started off with. So this is the overall way in which you undo the operation such that you're able to recover R starting from delta and R. So that. And overall, like knowing this constant of integration is very important before doing the operation multiple times. Because if we, for example, just apply S directly on this array that has an unknown constant, then you would see that like you get like 0, 0, minus 1.4, minus 1.5, and that is like quite different from the final answer that we get. So it's very important to like recover these unknown constants as you go along in the algorithm. So now I'll actually talk about a way that you can recover these unknown constants by leveraging the specific structure that we have in this problem. Are there any questions so far?
Sorry, I'm a little confused. So what are we trying to establish?
Sorry?
What are we trying? What's the big goal?
Yes. So like the big goal is to go from those samples y sub k. So we first had like a function or a signal x of t. We applied the modulo operation to that to produce y of t. Then from y we have from y of t we have the samples y sub k like discrete samples, and from x we had x of k. So we wanted we only like at the ADC we only observed the samples y sub k, like we only observe y of t. So you want to recover the samples x, knowing only y. So that's what we're trying to like our final goal is to recover x sub k, and the way we're doing that here is by first recovering that the r that was like defined. So r is like the difference between x and k. Once you recover r, then you can just add what you know in y plus r, and then that will produce your estimate of x. So that's the overall goal. So I will let like the unknown constant. So if we have like first of all we start off with the nth difference, then we go to like n minus first difference, so on, like and small n difference all the way to delta r. So I will let the unknown constant at step n, I will let that unknown constant to be 2 lambda times m sub n, where m sub n is also an integer. And the reason why the constant is in this form is because, as I mentioned, like r only has values that are multiples of 2 lambda. So similarly, any of the finite differences also have values that are only going to be multiples of 2 lambda. That's why we let the unknown constant to be of this form. So what that means is, if you apply the anti-difference operation, if you apply that to delta n r at index k, this will be equal to delta n minus 1 of r index k. This will be equal to this plus this unknown constant 2 lambda times mn. That's like the way that this is this unknown constant is defined here. So specifically, like using this relationship, if you were to, let's say, apply the operation s on both sides one more time, then like writing that side over here, that will mean that the n minus second finite difference of r, that this is equal to applying s 2 times, so denoting that by s squared of this. Question? Okay. Plus, so if we apply if we apply the anti-difference operation to a constant value, that will basically be this constant value times how many times you did that, so times k. So basically like integrating a constant. If you do that, then you obtain a factor of, let's say, x. You're integrating on x. So in this case, you will just have 2 lambda times mn. We have at index k, so we have times k, and then we have plus the unknown constant for step n minus 1. So we have like this relationship. Now, so now if we consider using this relationship, if we just consider this term, and we consider the values of k equals 1 and k equals j plus 1 for some j that I'll mention what that is soon. So basically what that will give you, if you consider the difference between those, so you consider this value, index 1 minus index j plus 1, then this will just be equal to like subtracting those sides, 2 lambda times mn times k times j, because you have like 1 and j plus 1, plus this term 1 minus plus 1. So now like our overall goal is we can upper bound the infinity norm of this term using the fact that r is just x minus y, and then using the bound that we had before on like using the bound that we had before on the finite differences of x. So like I won't go over the full details here because it takes a few more lines, but basically like eventually you're able to show that the infinity norm of this difference, like using those bounds and also using the triangle inequality, you can show that this is going to be upper bounded by this, the same term that we had before. But now we have like the n minus second, so we have the power n minus 2, and then plus 2 to the power n minus 1 times lambda. And then if you choose your TS to be less than 1 over 2 times 2 pi e times b, and we know like our n will always be less than or equal to capital N. So using these two facts, you can further simplify this one. So the infinity norm will be upper bounded by 3 times the infinity norm. Oh, sorry, there's also the term that we had before. So 3 times the infinity norm of your continuous like signal x of t. So that's like that's the overall bound that we'll use, and the way that bound is used is so because of this like bound, that means that this value is always like between minus 3 times this, or 3 times that. Right, there's also a fact. So that will mean that going back to this term here, this difference of two values. So s squared. That means that this is going to be in the interval of 2 lambda mn times j, plus or minus that infinity, the upper bound on the infinity norm. So plus or minus 3 over 2 times this value here. And then from this fact that this lies in this interval, you can rearrange both sides, and you can obtain that the unknown value that we have, like the unknown mn, that this lies in the interval 1 over 2 lambda j times that difference over here, 1 minus this plus or minus 3 times the infinity norm of x. So now we're able to like choose j because j can be any integer value. So we will choose j to be equal to if we choose j specifically to be equal to the value 6 times this divided by lambda, then you're able to see that this like difference that we have over here, that will just be like 1 over 2, 1 over 4. So the interval over here will be basically it will have length, like this term will eventually become plus minus 1 over 4. So that means the interval is like of length 1 over 2, and that would mean that you're able to like uniquely recover this mn because it lies in an interval of length 1/2 that only contains one integer. We know that m is an integer, so that's how we recover these unknown constants. And so by repeating this operation multiple times, like first applying the anti-difference, then like computing this value of mn, we're able to like go all the way down to the delta of r, and then finally all we'll do is we'll apply the anti-difference operation one more time. So you apply that on delta r, that will like produce our final estimate for r. So basically, like in this case, we're not able to apply the same technique because this technique relies on n being more than 2. So our final estimate for r will be equal to the correct value of r, plus again some unknown constant. So like this plus 2 lambda times m. Question?
But it was we can't do this for small values.
Yeah. So overall, like we're able to do this for n bigger than 1. So like we're able to like go like for all these steps here, starting from capital N all the way down to delta r. All of these intermediate steps, we're able to use this method, and we're able to like recover those unknown constants along the way. But yeah, so B is the bandwidth of the signal. So like everything, yeah, like as long as you satisfy this condition on your sampling period. So the sampling period is a multiple of your bandwidth. That like the bandwidth is kind of like an input parameter to your algorithm. So then you're able to like do this operation. Because this bound is not dependent on the value of n overall. So you're able to compute that unknown dot. So yeah, like when you do it the last time, then the same technique cannot be used. However, like you're still able to like recover your R up to this unknown. So using this R hat, we can finally like compute our X hat to be equal to like the values that we know, yk plus our estimated values over here, R hat k, and then this will just be equal to like xk again plus some unknown constant. However, this unknown constant is actually not a big deal now, because even if you have like the ground truth information for a single sample, because m remains the same, like m is not a function of your index, so you're able to recover that only with a single true value unknown. So overall, in this way, like starting only from knowledge of the y's, we have recovered the x's that we wanted to. Once you have your samples x, you're able to go directly by using the Shannon sampling theorem. You're able to go directly to your original input signal x of t. So yeah, that's how the overall algorithm works. In terms of the additional conditions that we require, the only new thing is this bound over here, which if you like invert both sides, it's equivalent to fs being more than. Let me just write it. So the only additional information that you need is that your sampling rate is bigger than 2 times 2 pi e times bandwidth. So if you like recall, in the Shannon theorem, all you had was 2 times b. Here we have this additional factor in the middle of 2 pi e. So that's like so this additional factor is kind of like a drawback, or kind of like an additional assumption that the algorithm has, because obviously this algorithm is doing a more difficult problem than the standard sampling theorem. Is also like trying to recover the original values using only like modified samples. So yeah, that's all for my talk. Thank you for listening, and I'm happy to take more questions now.
Out of curiosity, why is it that our sampling operation, whatever is doing it, cannot record values outside of a certain interval,
Yeah.
but somehow can record them if we reduce modules?
Yeah. So basically that limitation that comes from the underlying like hardware and underlying like circuits that are used for this operation of sampling. So basically when it's sampling, it's only able to record correctly values up to some maximum or some minimum. And over here, because the way this modified system works is we first are able to like apply this modulo or this like folding operation. So like the sampling itself, like the recording of the values, that's only done on a signal that has a finite like range. So the only limitation actually that comes in the operation of the sampling or the recording of the values, and like things before that, like operations that you do before that sampling operation, those are not like affected by these limitations.
What kinds of operations are these?
So over here, for example, like that operation would be the modulo operation. That's like applied before the sampling stage, such that like when we sample, we don't have any limitation, but our input can be an arbitrary signal.
So, what is an example of a concrete limitation that is preventing us from recording values outside of the beat?
Yeah. So for example, there's something like in in circuits and hardware, for example, there's something known as like saturation. So overall, you provide like some, let's say some voltage to like your hardware. So for example, like we have like 5 volts, or we have like 110 volts from the main supply. So overall, like any any let's say voltage values beyond that range, it's like are basically not possible for your like hardware to even like measure, because they lie outside the main operating range of that device, just which is limited by like input like voltage levels, for example. So that's why we have like this like a finite dynamic range.
But we can construct some module that will cut the signal or reduce it.
You can actually so actually like it is possible to have a module to have the module operation be be realized completely in hardware. There's actually like a specific technique from the circuits literature that actually like is able to do this operation like on an analog input signal value. Any more questions?
Yes, this is a constructive method.
Yeah.
Like the original sampling from the reduced sampling.
Exactly.
But we were just trying to prove that this is unique.
Yeah.
I guess we can't prove that it exists because it doesn't always exist. We were to just prove that it's unique. The equivalent to proving that no sampling whose values in discrete whose values are all integral multiples of lambda, that any such sampling must contain some high frequencies outside.
Yeah, exactly. So actually there is like a separate there's a separate line of work that's actually like studies like more from a theoretical, like more from a non-constructive approach. So they actually have like shown conditions on like the uniqueness that is needed, and they're actually also like one of the main limitations that I mentioned here is that we need this additional like factor when we're sampling. So like that paper has actually like shown that theoretically like it's even possible just using like a standard like the standard Shannon rate of 2B. It's still possible to like do this thing. However, their proof is actually like not a constructive proof, so they don't actually like provide any concrete algorithm, but theoretically like this problem is actually even possible even without this additional factor. So there's both conditions on the uniqueness as well as like on reducing this sampling rate required. Thank you.